Okay, Earth science time today. Again, we are resuming our discussion about the rock cycle, and we had talked. If you remember right, I'm going to relabel this rock cycle. I think last time I did it in blue. This is going to be black. Yes, the color of death. That's right. But also the color of many rocks. Remember last time we talked about what a rock is and how rocks change because the nature of all things is change, and we talked about specifically how many different types of rocks can become other types of rocks. I hope you remember those. We did also talk about specifically igneous and metamorphic rocks, although we have a little bit more detail to go into with at least metamorphic rocks. But today we're going to talk about, do you think, sedimentary rocks, sedimentary rocks. What processes from our rock cycle diagram, either from your bell work or from the discussion on, was that Friday or it must have been Friday? What processes are associated with sedimentary rocks?
Erosion and weathering.
Yeah. So first, one of the processes that lead to sediment itself, hence the word sedimentary, are weathering, I'm going to underline sediment here, weathering and erosion. And we defined weathering as, and remember we had this definition, I asked you to write it down, I don't think I did, but no, it doesn't have to be chemical decomposition, but that is one of, okay, so I'm not saying Hunter's not wrong, he just hasn't said the whole truth, he's specified. Yes, when rock material, which we defined, is turned into sediment, by chemical decomposition perhaps, but also by physical decomposition. Justice, what did you have to say? Okay, so chemical decomposition would be, it's breaking down what it's actually made of. So instead of being, for instance, maybe instead of being calcium carbonate like limestone is, it is chemically changed to calcium chloride and carbon dioxide, for instance. So that's a different thing. Whereas physical weathering, we should probably talk about these. Physical or mechanical weathering, two phrases for the same thing, and then chemical. So as I just said, in chemical, the composition changes. For example, another example, rusting. So rocks that are made of iron or have iron in them can oxidize, and that becomes iron oxide. And that's a different thing. So it was iron or some iron mineral before, and now it's iron oxide. It has a different composition. That's a chemical weathering. It is still breaking down or changing, but it's changing composition, so it's chemical. Whereas with physical or mechanical weathering, that is just, I'm just going to put breaking. And of course, there are methods by which this can happen. How could a rock break? Okay, that's a great example, Gunnar. If Gunnar takes two of these rocks, like Caveman, like Cro-Magnon Man, and Gunnar smash, he just does that. Does that count as weathering? Because Gunnar did it? Yeah, in Earth science, a lot of times in things like maybe in biology or physics, we kind of pretend like human beings are not part of the equation. Like okay, if a human being does it, it doesn't count. That's a different thing from nature. But at least in this context, with weathering, we do count human activities as weathering. So human activities do count as weathering. They're a kind of weathering called biomechanical, like from life. So biological weathering. What if a little worm burrows its way through some sediment? Yeah, that's biological weathering also. Can it break in other ways besides Gunnar or a worm? Mm-hmm. What? Rain, yeah. So the rain can, for one thing, water is very, I shouldn't say very, but can be, depending on what else is in the water, can be very good at chemical weathering, like acid rain. Acid rain is as water goes through the atmosphere rich in carbon dioxide, the water becomes, or absorbs carbon dioxide, and it becomes carbonic acid, and that acid can change the chemical composition of some rocks, specifically limestone, or including, and what's the word I'm looking for? Notably limestone. There's a lot of limestone around, and so it's affected by chemical weathering a lot. But also the rain itself, just hitting a rock, even though it's just water, over time can break down that rock mechanically. What else can cause mechanical weathering? Yes. Okay, Gunny, you already had one, but let's hear another one from you.
If a rock is super high up on a cliff and it falls and rolls down and it hits the ground hard,
Yeah, is that also erosion? Yeah. What was the definition of erosion? Let's switch gears a little bit. So this is where rocks break down to sediment. Transportation. This is the transportation of sediment. Are these two things mutually exclusive, meaning are they always different from each other? No. One does not exclude the other. It can be both weathering and erosion. Is every weathering erosion? No. But are some weatherings erosions? Yeah, and vice versa. Not every erosion is associated with weathering, but some are. So, yeah, how can sediment be transported then? Okay, so there's a list, and we'll talk about these in more depth later on in a different unit, but in case either there's not time or I forget to mention it, or so I can refer back to it, I'm going to give you the list. Let's not put rain. Let's put a different thing. Wind. Okay, good. So I'm going to put in one column, I'm going to put, I don't know, I'm not going to do it like that. I'm going to put what a normal American English-speaking person would put, and then I'm going to put its fancy science name. For this one, it's eolian. Eolian. So erosion, the transport of sediment by the wind is called eolian erosion. Okay, what's another kind? What's another way that sediment can be transported?
Water.
Okay, there are lots of different kinds of water, so let's be more specific.
Let's say water like river.
River, good. River. Let's say water like river. Water like river is called fluvial erosion. Okay, what else? What other kinds of, let's stick with the water for, let's get all the waters out at once. No, rain doesn't really carry sediment usually. Ocean, you probably already know what I'm going to put for the fancy word. What? No? Ocean, we could say. I mean, it's not that people don't say ocean. But come on. No, what's the Latinate word used to describe the ocean? Marine. You're right. Okay, what other kinds of erosion are caused by water? Don't do that. I'm trying to talk.
When rain comes down.
No, rain doesn't really count. It doesn't really carry sediment. So there are kinds of, like, I'm going to put over here rill and gully. I guess that's kind of in the same, it should be in both categories because no one calls it anything other than that, and these aren't really normal words that we use. But rill, this could be the word rice, the way my handwriting is, but it's not. It's rill. Rill and gully. So as rain falls and carries sediment with it, a rill might form, which is like a kind of little small channel through which, you've seen these probably in people's yards or in the buttes, where as rain falls, it digs out a little furrow, and that's called a rill. If the rill gets big enough that it is permanent, it's called a gully, and you've probably heard of or seen gullies out on, I don't know, government land or when you're on your ranch riding around your four-wheeler. Gullies are permanent but dry, or usually dry, depressions in the ground, and that these kinds of erosion, a rill might become a gully, and then a gully might become a stream, or which we would call fluvial erosion, river or stream. What else? What other kinds of water, though? We're still doing on water, Hunter.
I have a comment that's not about water.
Okay, I don't want to hear the not water yet. Is it about rill and gully erosion, though?
Kind of.
So this is how when people kept saying rain, this is really the kind of erosion that results from rain. Let's hear yours.
So in Arizona, there's like heat cracks in the desert.
Yeah.
And they do fill up with water, but it's caused from like immense heat. So is that a form of weathering?
Why does everyone think that since Hunter is talking that we should all talk at the exact same time? Let's all be quiet. No, so the mud cracks that you're talking about are expansion and contraction of sediment because of when it's wet, it takes up more room because there's water in it, and then when it dries. And so there are rills and gullies formed in and through that process, but they're not the exact same thing. What other kinds of water erosion are there? Come on, you can think about it. What? I put river with streams. They're both called fluvial. Lake, there you go. Lake. This kind of erosion is called lacustrine. Lacustrine. Okay, one other. Think about the other state of matter that water commonly is in on Earth's surface. But what do we call a big ol' ice? Glacier. Yep. Glacier, and we call that glacial. Yep, this one's pretty easy. Glacial.
Okay, I know another one.
Okay, what's another kind of erosion in general? Yeah.
Rain. If I take a rock and I throw it.
Okay, so bio. You're a bio. You're a biological thing, and so bio erosion or biological erosion. And then I'm also going to put on here, if it's caused by gravity, we call it a mass movement. And guess what? Most of these, not really rain, not really wind, are caused by gravity on some level. That's where they get their energy from. Where does wind get its energy from? Yeah, atmospheric changes, the sun, basically. But gravity causes most of these other ones on some level, and gravity is called a mass movement. And there are different kinds of mass movement, including rock fall, landslide, slump, creep. There are others, but these are kinds of mass movement. Where the sediment is moving, maybe not only, but mostly through the effects of gravity. Whereas these other ones are caused mostly by water, the mass movements are caused mostly by gravity. Although gravity is the energy source for these, and these might involve water, but we talk about what the primary source of its erosional effectiveness is. Okay, so those are different kinds of erosion, the way sediments move. And then what is the process that takes all of this, the kinds of weathering and the kinds of erosion, and makes them into actual sedimentary rocks? So this is how sediment is formed and moves. So this becomes sediment. But we're not only talking about sediment, we're talking about sedimentary rocks. How does that happen? Yeah, compaction. Compaction, what does that probably mean to you? Yeah, squish. It becomes compacted. And what is probably the source of energy for that? No, yeah, mostly gravity. Pressure from what? Gravity pulling it down, but what's pushing it down from on top? More sediment, not human hands. Just a pile of human hands. It's just a crypt of millions of human hands pushing down the rock. No, it's sediment. It's the hands of the earth, maybe. It's tons of sediment pushing down other sediment, compacts it. Okay, and what else happens? And then sometimes, it's not always compaction either, but sometimes it becomes cemented. Cementation. So it becomes cemented. With the way that usually works is kind of like cement that we as human beings might use. The cement is another, it's kind of a Latinate word for glue. It just means that it sticks things together. And the way this works in nature usually is that some mineral is dissolved in the water. Most water on the ground will have minerals dissolved in it. And then as the water evaporates, just like in your crystal lab, as the water evaporates, the crystals will grow out, and those crystals growing between the sediments, it would be better if you paid attention instead of talking all the time. As the crystals grow between the sediments, they're stuck together. They're cemented together. And these two things together can form sedimentary rocks, and that process is called lithification. The suffix ification means the noun based on how something changes. What does lith means? It's becoming stone. Yeah, becoming stone. So changing from sediment through lithification, through compaction and cementation to sedimentary rock. Now here's the other thing we are going to talk about with metamorphic rocks. If it gets so compacted that it's becoming metamorphosed, then it becomes metamorphic rock. And so in what we might call a normal sedimentary environment, these things, with just the pressure of overlying rock layers to a moderate degree, it's lithified. But what are some ways that it might be metamorphosed instead? The big brother of lithification on a greater scale is metamorphosis, right? Greater pressure and greater heat. Remember, there's still some heat with this. There's heat in the environment. But if the heat and the pressure get big enough, it becomes metamorphosis. What are the ways that can happen instead of just being lithified? We already said them on Friday, kind of. But okay, so it could be due to the presence of magma. We called that. These are the different kinds. We're changing gears a little bit, but the types of metamorphism. I said them out loud on Friday on the last video or the last discussion, but we didn't write them down. The types of metamorphism are if it's touching magma, rock that touches magma, but isn't itself melted, is said to be undergoing contact metamorphism. It's touching. It's in contact with the magma chamber, and so it's touching. It's touching it, and so it itself is provided heat. It's under pressure also, and it metamorphosizes. What happens if it melts? Well, then guess what? It's not going to be. If it melts, it's not going to be a metamorphic rock at all. It's going to be magma, and then when that cools, it'll be igneous rock, right? So what's another kind of metamorphism? I'm going to just label them all one. Regional is due to what? What major force on planet Earth might cause a whole area, a region of rock to be metamorphosed as plate tectonics. So we kind of have three energy sources for sedimentary, metamorphic, and igneous rocks. Although they're not specific to each one of those, they're not in that order. We have mostly the sun, gravity, and plate tectonics. Those are the major energy sources for the rock cycle. Okay, what other kinds of what's number one on the list of types of metamorphism?
Number one.
What's another one? I guess that works. What's another one? We have all these ones. What's another one? Did you say what?
Blowhole.
Wow. No. I'm trying to think of how that would work. I'm just going to tell you.
Let's do ISO.
Hydrothermal, which means if there's very, very hot water, very hot and very pressurized water, this will form things like veins of minerals where like there's splits in the rock and super hot water carrying deposits of minerals will gush through those splits in the rock, and then as that crystallizes, you'll be left with...
But doesn't water evaporate?
Yeah. So you're because it's too hot, right? But it's also under immense pressure. So even though the water might be thousands of degrees, it's also under a lot of pressure, and so it gets, even though it's hotter than on the surface it would boil, it can't because it's under so much pressure. And then what's number one? This is the coolest one. This is the sexiest one, is impact metamorphism, where a meteor smashes into the planet, and that impact makes some of the rocks melt, even some of the rocks vaporize, but the rocks that, again, like contact metamorphism, aren't melted or vaporized, are changed. They're metamorphosed. This one's extremely rare. Obviously, it only happens when there's meteor impacts, but it does happen. So all of these ones are the types of metamorphism. So, and those are, we talk about that because they're related to lithification. These are just big, hotter and more pressure versions of lithification, and these result in metamorphic rocks, which we talked about. Foliated and non-foliated as the categories, and we talked about that in the last discussion. And then as a reminder, we talked about the kinds of igneous rocks. We did that very, very quickly and at the end of the lesson, so make sure you look in your book about the kinds of igneous rocks too. We did list most of them, but there are a couple that aren't there, and that's why we're going to do that lab about identifying rocks too. We'll talk more about the types of rocks in all of the cases, sedimentary, metamorphic, and igneous, in the lab. But for now, do you have questions about either the types of metamorphism or the ways that sedimentary rocks in general form? Good. Then let's move on to the types of sedimentary rocks, and then we'll be done. Can I erase this about sedimentary rocks? Can I erase about sediments themselves?
I wish not.
What?
I wish you would.
But I already did, so...
Please don't. Can you don't do
You
that?
have a choice.
I don't have a choice.
Please don't.
I'm not the master of my own fate. I have to erase. I am the total eraser. I must be erasing.
No.
You missed one spot. That's really bothering me.
Let me make. I'll just draw a table over top of it. Okay,
Oh my
so
God, you did it. Go.
these are the types of sedimentary rocks. They're largely broken up into, or mostly broken up. The big breakups are in clastic, chemical, and biochemical.
That says
Clastic. There we go. Clastic. Have you ever heard anything with the word, or with the part of a word clastic in it before?
No.
It's
Plastic. It's not unrelated, but
Not plastic.
I don't know what that is, so no. The things I thought you might have heard of, this was a stretch, but pyroclastic flow is when broken material comes out of a volcano. Pyro, fire, clastic means broken. You should write that down, probably. Clastic means broken. But the pyroclastic flow as it comes out of a volcano is the fire and broken bits of a volcano that come out. Pyroclastic, fire and broken. Another even stretchier stretch is you might have heard of iconoclasm, which is where in the Renaissance or in the Middle Ages, the church would break icons because they thought they were idolatrous images, and so iconoclasm, the breaking of icons. But no, you haven't heard of those. So clastic just means broken.
The only thing I remember is nice. This is a nice
Okay,
rock.
so the clastic rocks are judged by grain size. So I'm going to, since there's this little dot here, I'll just write grain size over the top of it. Grain size. Okay, so we have grain size there. And the grains the grain sizes in order. I'm going to put the finest ones on top, and then we're going to go down. The finest grains are called clay, followed by silt, followed by sand, although there are fine and coarse sand, and then gravel. So these are the sizes of grains. The smallest is clay, the biggest is gravel. I mean, there are others. There are boulders, etc. down here, but these are the ones we mostly talk about. Grain size, grain size, grain size. Gravel, gravel. Or we might say pebbles. Gravel or pebbles. And the rocks that are formed from the lithification of these sediments, right? These are sizes of sediments, sizes of grains. I'm going to put that on here. Sediment / grain size have different names. Clay-sized sediment formed into a sedimentary rock forms shale. Silt forms siltstone. Oh. Or mudstone. Siltstone or mudstone. Sand, can you guess?
Sandstone.
Sandstone. And then gravel or pebble size is either going to be, depending on if it's angular, breccia, or if it's rounded, it will be called conglomerate. I want you to be quiet. So these ones, depending on if it's angular or rounded, will be called a different thing. So if it's angular chunks that are gravel or pebble-sized, breccia or breccia, depending on how Italian you are, or if they're rounded, they'll be called conglomerate. And what do you think determines whether in general an area has these different size sediments or different size ones? What determines the size of the sediment in a particular sedimentary environment? That is in no way an answer to this. Conglomerate. Now, but answer my question. What's going to, for a given location, like the buttes outside of Crawford, what is going to determine if what we find is siltstone or shale, for instance?
The weight is analyzation.
You guys are just saying absolutely random stuff. It's determined by the erosional medium.
Erosional medium.
What are the erosional media? What are the erosional mediums? That's not a right word. Media is the correct plural. But what are the erosional media? Yeah, those ones you have the list of. So draw a list. Mine's gone because I erased it. But draw an arrow back from this erosional medium here back to where you wrote down the erosional media. So greater energy. This is the most important principle of sedimentology. Greater energy media. Again, what's the word media mean? It's the plural of medium. So greater energy of the erosional medium means bigger sediment. More energy can carry bigger sediments. Okay? More energy means bigger sediments. So of those, which do you think, this might be kind of a trick question, we'll talk more about it later, but which do you think of those erosional media generally has the least amount of energy?
I don't know.
Okay, it could maybe wind, depending on the what of the wind. The speed of the wind. Okay, so which of those is probably the slowest moving, the lowest energy of the water media? No, look again. Lake. And so what kind of rock would we expect to find where an ancient lake used to be? Big grains or small grains if it was low energy? Small. And so shale means if we find shale somewhere, it means that area was likely an ancient lake or an ancient inland sea. Like what's the name of the shale that everyone drives through Gumbo and they're like, oh, I got stuck in the Gumbo. Do you know? You know what I'm talking about though? Up there north of town, the Gumbo, that's pure shale. And that's where the ancient inland sea was when the dinosaurs were roaming the earth, right? And so the way we know, one of the ways we know, there's multiple evidences for this. One of the ways we know that was shale one of the ways we know that it was an inland sea is because we find shale deposits there. What if we find gravel or even larger boulder-sized sediment? Yeah, a river maybe, or What else could it be from that list of erosional media? Do you think?
The one with the G.
No? Maybe a gully, but probably not. I would say probably glacier. Glacier is what we normally associate with bullet, but glaciers have a lot of energy. And another principle of sedimentology is longer time spent in the medium equals rounder sediment. The longer it spins in the river, the rounder it is. So does anyone at their house or have ever seen something called river rock that you can buy like from Home Depot and you just put it in your yard instead of having grass there? Yeah. There's river rock, and what does that look like, or what does it feel like? Smooth and round. And that's because that rock came from can you guess? River. And it spent a lot of time there, and so as the water, sure, but mostly as other rocks knocked into each other, the corners get knocked off. So if it starts out like this, and you have two of them, and you bonk them together, the corners get knocked off, and eventually more corners get knocked off, and you get up to little round rocks. The longer they spend in there, the rounder they get. That's one of the principles of sedimentology. And so we can't go back in time to when there were dinosaurs. Do you know that? We can't go there, but we can find out where dinosaurs used to live by using things like, the Pier Shale was where an inland sea was. So this is it's important that we know about these kinds of rocks so that we can learn about the past, about ways things used to be. I think let me look through this to make sure I didn't miss anything. One of the things we should talk about, for one thing, we should definitely talk about chemical and biochemical sedimentary rocks also. But one of the things we should talk about while we're in clastic rocks is that there's this principle of bedding, where I'll just define bedding, the way sediments are laid down, like in a bed, by an erosional medium. So the way they're laid down, maybe we see in a rock layers of coarse sediment, and on top of that is layers of finer sediment. That tells us about the erosional environment. The way that it's laid down by the medium is called bedding. So that bed tells us something about it. And that's true of clastic rocks that are normally found from these kind of erosional media. Now, let's briefly talk about, I'm just going to do this in a different color. I want to erase anything as you're probably still writing. Let's briefly talk about chemical sedimentary rocks. These are usually the ones that form from solution. So like those crystals that you're growing in the lab, that you did for your mineral lab that are still growing, most of them, those would count as, well, for one thing, they're crystals, so they very well may be minerals, but they also count as chemical sedimentary rocks. They form from a solution. And these ones are limestone, if it's from calcium carbonate, CaCO3, or chert or flint, if it formed from silicates. So check it out. Here I have for you some rocks, hopefully. This is a piece of limestone. This rock formed when calcium carbonate that was dissolved in water, the water evaporated and the calcium carbonate was left behind, like in a cave. Have you ever been to a cave? Raise your hand if you've been to a cave. The rocks, the stalactites and the stalagmites that form in a cave are formed through the process of chemical sedimentation. I'm going to pass that around. Gunnar, you should wake up. Okay, and then this one is an example of the rock chert. So silicates are not normally very easily dissolved in water, but they do dissolve in water. And when the water evaporates and crystallizes out, we get this really, really, really smooth chert rock. And if it's light, it's chert. If it's dark, it's flint. They're the same rock, but they're not the same name. If it's light, it's chert. If it's dark, it's flint. So that's chert. That's a chemical sedimentary rock. And then what do you think? I'm going to do this in a different color. What do you think would be true of biochemical sedimentary rocks? Formed from what? No. No one's listening at all anymore. Emma is. She's taking notes. Other than Emma, I'm going to repeat it. What do you think biochemical rocks form from?
Like how diamonds do? Yeah. They form how diamonds do. They form how diamonds.
What do you think biochemical sedimentary rocks form?
Oh, we make them in a lab.
Life. There we go. Thank you. Form from life. So living things. So So maybe things like we could have coal. Remember we watched in that video about how coal forms, which is from the remains of dead living things that were pressurized, right? That were lithified. Also, things like fossiliferous limestone, which is limestone that bears fossils. That's what fossiliferous means. Or a rock made entirely out of small fossils, usually of marine organisms, called coquina. And I have one example of that here. Where is my example of that? Oh, it's this. This rock is made of fossils. This is a sick rock. I love this rock. I'm going to pass it around. This rock is made out of just fossils and fossils and fossils piled onto each other, and it's called coquina. Don't show it to Ethan. And let me show you an example also of what. Can you guess what biochemical sedimentary rock this is?
That's obsidian.
This is coal. This is coal. So pass that one around too. This is another. This is not a biochemical. This is another chemical sedimentary rock called gypsum. This is calcium sulfate that was dissolved in water. This is what drywall's made. I'm going to pass that one around too. This one's gypsum. And then the last thing we have. This talk about biochemical rocks reminds me. In what rock type, sedimentary, igneous, or metamorphic, do we usually find fossils?
Right, stop talking.
Sedimentary. Usually only sedimentary. There are examples, but they're rare, of metamorphic and igneous fossils. Why? Why would we mostly and only find this? Yeah, because the process of forming sedimentary rocks is relatively gentle on fossils, the remains of dead organisms, whereas metamorphism and igneous are not.